So we're going to look at what's called mathematical induction today. Everybody needs to listen. And really what mathematical induction is used for is to prove what are called mathematical generalizations. They're sequences, and that's what we've been studying. And it's really to prove that the nth number or the nth term in the sequence is going to be true. So for instance, we've looked a lot at, the first 10 terms or, the 100th term, but we want to prove that this works to the 365th term or so forth. And that's really what this is for. So you're going to see these are your three important steps here. We've got step 1, which is called the anchor. And we just have to prove, and we'll go through all of these with 3 different examples, prove that P sub 1 is true. So we're going to prove that the very first term in the sequence works for the pattern that they give you, or the rule or the function, which however you want to call that. And then we're going to do something that's called the inductive hypothesis. And all you're going to do is change every n that you see into a k. Kind of seems like a wasted step, but there it is. And then you're going to prove, then you're going to say if P sub k is true, which is really your P sub n term, then you're going to prove that P sub k plus 1. What term is k plus 1 in relation to k? How are they related?
It's the next one.
It's the next term. So we're going to then prove that the next term also works. And so here's what it looks like. So here's example 1. And so we're going to do step 1, which is the anchor step. And we're going to prove that the first term works. So as you look at this, we've got, if I were you, I'd take a highlighter. I can't highlight on this, but if I were you, I'd take a highlighter and I would highlight all of this right here. It's saying that the sum of all of the terms, and we're missing obviously some of the terms in here because this is an infinite sequence, but the sum of all the terms equals this. And this is just the last term of the sequence, but this is the rule for the whole sequence. So if we were doing sigma notation, this would be the rule that you would use to find each of the different terms. But all of this can be replaced with n squared because they are exactly equal. That's going to become important in one of our steps in a minute. But we're going to prove that this term 1, the value of this term 1, which happens to be the first term, works in n squared. Every single one of my examples, the first term has a value of 1. Is that always the case? No. So you need to understand that we're not always plugging 1 in for n, per se. Oh, you'll see here in a minute. So we're going to prove, let's see if I can actually write legibly. We are going to prove the first term equals the rule. For instance, we're going to take a sub 1 and set it equal to n squared. Well, what is the entire value of a sub 1? Yeah, so this is the entire value. This is a sub 1. So that's why we were replacing the left side with 1. If the first term had a value of 5, I would be putting a 5 right here. So I need you to understand we're not always putting a 1 on the left side. It's going to appear that we're always putting a 1 on the left side because each one of my examples has 1 as the first term. So if you need to write yourself a note that this is whatever value that first term is. And so that is equal to n squared. Well, what is n? N is 1, not because the value of the first term is 1, but because it's the first position in the sequence, right? So 100% of the time, we're going to be replacing 1 here into the rule. So here on the right side, yeah, you're always going to be putting 1 in because we're always proving that the first term works in the sequence. So you're going to prove that the left side equals the right side. This is a proof. So what is the value of 1 squared? So 1 does indeed equal 1, doesn't it? So this is true. And that's your goal. You have to have that left and right side. You can't skip it because we're showing that the left side equals the right side. And then part 2 is your inductive hypothesis, and we are going to assume the rule works, bless you, for n equals k. In other words, I'm going to replace every n in the above sequence, the above sum, if you will, with just the letter k. Seems a little goofy, but it is what it is. So here we go. We've got 1 plus 3 plus 5 plus 7 plus ... plus 2, and instead of n, we're putting in a k, minus 1 equals k squared. That's it. And then step 3, this is really the meat of it. We're going to show that the rule works, emphasis on the word show. So we're going to show that the rule works for for k plus 1. So everywhere we see an n, we're going to replace that n with k plus 1 with the exception of one thing. And here's the important part, and this is the part that you miss each and every time. So let's go back to what I said here. What did I say about this left side, this whole piece right here? Doesn't it equal n squared? So right here, this whole piece, I want you to highlight all of this. Highlight all of this right here. What's the value of all of this whole sum? K squared. And so we're going to, because obviously if it equals n squared, it must equal k squared, right? So we're going to start off with, and we're going to do it piece by piece. So let's just do it the long way. So we've got 1 plus 3 plus 5 plus 7 plus ... plus parentheses 2k minus 1 and parentheses. Then you're going to put plus then we're going to do the next term. The next term after this, wherever you see the k, what's the next term after k? K plus 1. So wherever you see the k, you're going to input a k plus 1 for this next term. So we have to go one more term in the sequence. And so here's what it looks like. 2 times k plus 1 instead of the k minus 1. And then I'm going to put parentheses around that, or brackets, I guess, because I already have parentheses. And then that equals not k squared, but what? Well, k plus 1 squared. So on the right side, you are going to take that k and you're going to replace it with, because we have to prove that it works for the next term. In fact, let me move this over. So here's the deal. So this is exactly like the original, right? So I want you to highlight that. So this right here is exactly like the original sum. And that right there has a value of n squared, or not n, because we're not going to use n. No. Oh, well, I'll turn it into a k. I'll show you. That has a value of k squared, doesn't it? Because we're using k. So all of that is going to be replaced with k squared. And then this is the next term after this one in the sequence. This is the next term. And then we have to prove that all of this works for that next term. So in other words, the next term, instead of k, has to be k plus 1. So the right side always gets replaced anytime you have a k with that k plus 1. It just so happened we only had one of them here. And so the next step is to put k squared here, and then we're going to start to simplify this right here. So I'm going to distribute the 2 into that k plus 1. So I get plus 2k plus 2 minus 1 equals, and then let's go ahead and leave this as k plus 1 squared for right now, because I don't really want to touch that right side, if at all possible. So then we're going to simplify the left side. There's only one thing we can do. We can add those two together, right? And so we get k squared plus 2k plus 1 is equal to k plus 1 squared. What do you know about this? It's a perfect square trinomial. See how this is k squared and this is 1? They're both perfect squares. The square root of k squared is k. The square root of 1 is 1. 1 times k is k times 2 is 2k. It's a perfect square trinomial. It factors as k plus 1 squared. So the only next step that we have to do to prove it is to factor this as k plus 1 squared is exactly equal to k plus 1 squared. Once you show that the left side is identical to the right side, you're done. So remember when we were doing proofs before and you weren't allowed to touch? We were doing the trig proofs, sine, cosine, tangent, secant, cosine, all those kind of stuff. You couldn't touch one of the sides. Same thing here. Try not to touch one of the sides. There's a few examples where you might not be able to do it that way, but try not to touch the other sides. So sometimes we'll simplify this side here. Just simplify it as much as we can. So if there's 2 fractions, we simplify it into 1, that kind of stuff. So we'll look at as we go through here. So that's the general process. Let's look at the second example. So let's look at number 2. So instead of them having on this one s sub n is equal to, we just have the sequence, and that's fine. We're still going to do step 1, which is your anchor step. Here's where we want to prove that a sub n, or a sub 1, sorry, we want to prove that a sub 1 is exactly equal to this rule. So we're going to prove that a sub 1 does actually equal 1 using the rule. So here we go. A sub 1, whoops, that didn't work out so well. Let's try again. A sub 1 is equal to, again, this is the part on the left. So if I were you, I'd highlight that part. That part is exactly equal to this right side here, n times n plus 1 over 2, a much more complicated rule than we had in example 1. But this is the rule that we're going to put right down here. So we have n times n plus 1, all divided by 2, and that really looks like an h, but it's really an n. And what is the value of n plus n sub 1? This right here, it is a sub 1, sorry. A sub 1. And the value of a sub 1 is equal to 1. So that's why we're replacing the left side with 1. And then the right side, hi, get in here, you're wasting my time. Why am I replacing on the right side these with 1s?
Because the n is the first term.
Because this is the first term in the sequence, right? So this right side, the n is always going to be replaced with 1. On the left side, the only reason why this is 1 and not some other number is because the value of a sub 1 is 1. If that first term was 5, we would be putting a 5 here. So I have to keep emphasizing that because that's one of the things you're going to mess up. All right, and so then we're just going to do the math. So we end up with 1 equals 1 times 2 over 2, and doesn't 1 equal 1? So it's true. What's step 2?
Assuming the universe where n equals k.
Yeah, we're just replacing, replace. We're going to replace every n with a k. Essentially is what we're doing. So take the original sequence. In this case, we have 1 plus 2 plus 3 plus 4 plus ... plus, instead of n, we're putting in a k, equals, and then we've got k times k plus 1. Alright, so then this is all over 2. Any questions as to why we did that, other than it's stupid? I know that's what you're thinking, right? Oftentimes I skip this step, but Math Excel probably won't let you, so we need to talk about it. Alright, so then step 3, we are now proving it works for k plus 1, which is the next term. So wherever you see a k, with the exception of this very first part here, we're going to take this very first part, all of this, so circle all of this right here. What does all of this equal? No.
N equals n and
Oh,
plus
yes,
one.
yes, 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 I see what you mean. Yeah.
Oh, yeah,
So all of this, I was on the last problem, see, because my brain's elsewhere. All of this equals this right here, does it not?
Yes.
So I can replace all of this with this, but before we do that, we're going to put an extra step in here. So we've got 1 plus 2 plus 3 plus 4 plus ... plus the k, right? But then we have to do plus the next term. How do I write the next term? Yeah, because this happens to be a simpler rule than in number 1 right here, because number 1 it was what, 2k minus 1, wasn't it, or something like that? So here we're just going to replace that with k plus 1. So that gets replaced with k plus 1, because that's the next term, and so I'm going to put that in parentheses, equals, and if I were you, I would highlight this again with your highlighter to show that the only difference on the left side was we added the next term. So remember, this is an infinite series. Does this series converge or diverge? It converges? It diverges, because it just keeps getting bigger and bigger and bigger. Okay? And so the right side is going to be what? Because I'm replacing every k on the right side with...
K plus 1.
So this becomes a little bit complicated. So we've got a k plus 1 instead of the k. K plus 1, so we're going to put that in parentheses. Then parentheses, instead of the k, we have a k plus 1 plus that additional 1 all over 2. Right? So this is for the first k, because that's the next term, and then this is for the second k, and then we have the plus 1 over 2. Does that make sense? More steps the better, because you're least likely to get confused. And then we're now going to replace all of this with what again?
K plus
This whole rule, but with k's. So we're going to replace that. K times k plus 1. Oops, that's supposed to be a k. Plus 1 all over 2. Plus the k plus 1 equals. Then let's start to spruce up the right side. So here's where you can do a little bit of simplifying on the right side. So can't I add the ones together? All right, so we're going to end up with k plus 1 times k plus 2 all over 2.
Wait, is there supposed to be backs?
A who?
Backs.
Yeah, we're going to do one on the back, yeah. So even though I said we generally don't like to work both sides, you will see me doing some simplifying to help things out. So for instance, let's stop working the right and just look at the left for a minute. If I want the left, notice how this is a fraction over 2. I have my fraction over 2 here, but that I can't combine until it's got like denominators. So this currently has a denominator of 1, doesn't it? So to make a like denominator, wouldn't I have to multiply top and bottom by 2? So both top and bottom here get multiplied by 2. And so I'm going to distribute that 2, and I'm going to distribute the k. So the k gets distributed, the 2 gets distributed, and I end up with k squared plus k plus 2k plus 1. And because they're both over the same denominator, it's all over 2 equals. Oh yeah, sorry, plus 2. Thank you. Plus 2. So because I see where this is going, I am perfectly fine, but again, you'll have to kind of play with Math Excel a little bit. I'm perfectly fine if we simplify this into k squared plus what? 3k plus 2. And then this you can go ahead and FOIL out and see, will it equal k squared plus 3k plus 2, and just leave them that way. Or instead, because here's my thinking, if I do try to get this to look like that, I have to simplify this to the k squared plus 3k plus 2, and then I have to do an additional step to factor it. So I'm just saving a step. You can do it that way if you want to. Patrick?
Can I just not change the left side at all and change the
No.
right side?
No,
Why not?
because we need it in simplified form. And this would not be considered simplified form. Are you saying leave it just like this? And
Simplify it beyond that. I mean, like instead of changing the left side originally, just make the right side same as the left and the other way around.
you want to make this look like this before I put the red 2's in here?
Yeah.
No, don't. You'll never get it right in Math Excel. And I wouldn't generally accept it that way. And typically that's much more difficult. Typically. But let's not. We like to simplify things into one fraction if we can, or one polynomial that's factored. All right, so then the right side, if I were you, I would FOIL. So we get k squared, k squared. The k times 2 and the 1 times k does give you 3k. I'm totally okay at the pre-calc level that you were able to FOIL and add 2 like terms together. And then the 1 times 2 is 2, all over 2. So as far as I'm concerned, the right side is fully simplified done. And the left side just has one more step where we have k squared plus 3k plus 2 all over 2. And you must show that it does equal k squared plus 3k plus 2 all over 2. Do not lose your equal sign. So this now, left side looks like the right side. Check. So we have one more that we're going to do. So you're going to flip it over on the back and you're going to write it down. Any questions about that? No, it's online, or it will be online one of these days, so you can grab it from there. That's what happens when we're late to class. Page. So for example, 3, I don't have a lot of patience today, Jason. You missed why I don't have a lot of patience. It has nothing to do with you. I love you dearly. You're awesome. See, Jason, I'm smiling. You're not smiling. Come on, smile back. Make me happy. Oh, thank you. All right, so we're going to use mathematical induction. That's actually an M. Mathematical. And mathematical induction is used in calculus, so that's one of the reasons why we are going through it. Given. So we have S sub n is equal to 1 squared plus 2 squared plus 3 squared, you can see where this is going, plus 4 squared plus dot 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 plus n squared equals n times n plus 1 times 2n plus 1 all over 6. Essentially what you're just proving is a sum formula for an infinite series that has the rule of n squared. It's essentially what we're doing. We're proving that that rule works for the next term. So here we go, step 1. What's our first step?
Okay,
Oops.
so A1 equal to, what's that?
Prove the rule works. For A sub 1. So A sub 1 is equal to, what do we set it equal to? The n squared or the n times the n plus 1 times the 2n plus, which one?
It's the one on the right, the front.
The one on the right, this one.
Yeah.
The more complicated, you never set it equal to this one here. Okay? So we're going to set it equal to n. Oh gosh, I can't write today. N times n plus 1 times 2n plus 1, all divided by 6. So what is the value of A sub 1? 1. And we are going to put, for our purposes here, 1 squared, just so that you start to understand that we're not putting in a 1, I'm putting in the value of the whole term. And so that equals, for every n we're putting in a 1 because 1 squared is the first term in the sequence. So 1 times 1 plus 1 times 2 times 1. And yes, you have to have this step in there. This is a proof. More steps than less is always better if in doubt. So people don't like to show their work, tend to miss a lot of points on this. All right, so then from here you want to just show your math. So we've got 1 is equal to 1 times 2 times 3 all over 6. And from here, I'm okay with you just saying 1 equals 1 because we are in PreCalculus, and so it's true. But get it as simplified as possible until you're, canceling things out. And then the first and second step should be very easy for you because all you're doing is taking the value of the first term and setting it equal to the right side of the sequence sum and plugging in 1 in that right side, and it should equal the value of that first term. And the second step should also be easy because all you're doing is prove the rule works. Well, not prove. Show. I guess that's the word I want, show. Show that n is equal to k is essentially what we're doing. So we're going to write the sequence, but for every n, we're going to replace with k. So nothing really changes, right? Move it over just a smidge. All right, so I want you to circle all of this in the original sequence, the entire left side. What does the entire left side equal?
And this one,
Right, so the entire left side, and I'm not going to rewrite it, equals all of that this whole value here, right? All of this is equal to this. So that means that all of this is going to get replaced with this in just a minute. But for step 3, we have to put in the k plus 1. So show the rule works for k plus 1. So before we can use k plus 1, we have to write the original sequence that we see here. So I'm going to write all of that in black. So 1 squared plus 2 squared plus 3 squared plus 4 squared plus dot 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 plus k squared plus. Now what do I put? So then I put parentheses, and then I'm going to use red for this. So we're going to put in k plus 1 wherever we see a k now. Squared equals. You always take whatever this is and write it again. So whatever this is, write it again, but put the k plus 1 in there. And so then on the right side, wherever you see one of these green k's here, we're going to put in a k plus 1. So we've got k plus 1. It gets a little long. So that's in parentheses, times 2 parentheses, k plus 1, and parentheses, oh wait, I did that one early. Sorry, jumped the gun. How about we put in k plus 1 plus 1 parentheses, and then 2 parentheses, k plus 1, in parentheses, plus 1, in parentheses, all of that over 6. Do you see how it can get complicated? But you just go little bitty pieces at a time. So what does all of this get replaced with? All of this, right? So all of that gets replaced with k times k plus 1 times 2k plus 1 all over 6. Then we have plus the k plus 1 squared equals. So we just simplified that whole sequence. We got rid of all the pluses and the dot, dot, dot. And it equals, and on the right side, we're going to simplify anything that's in these parentheses. We're going to just simplify as much as we can as we go. So I am going to distribute this, and I will, Patrick, you'll be happy, skip a step here, because when I distribute the 2, I get 2k plus 2, and I'm going to add that to the plus 1 as I go. So my right side is k plus 1 times k plus 2 times 2k plus 3, all divided by 6. Is there anybody that doesn't understand where I came up with the k plus 2 or the 2k plus 3? Okay. So I kind of like the way that looks. And because it's somewhat simplified, I might want to multiply perhaps 2 of these together at one point and just leave it unmultiplied. We'll have to see what happens here. But first and foremost, I can't combine these two in one fraction because this is one fraction until what? Until this has the same denominator. And in addition to that, I am going to want to square this out. So one of my first steps is going to be to multiply this by 6 and this by 6. So on the left, I'm probably going to multiply these together first, and then I'll distribute the k on my next step. So I've got k times, and if I FOIL, I've got k times 2k, which gives me 2k squared. Well, why might I not? Well, yeah, I guess I'll do that. We'll go ahead and do that. And then I've got, bless you, k times 1, which is k, and 1 times 2k, which is 2k. So k plus 2k is a 3k. Yeah, I caught it. I got interrupted. I interrupted myself. And then 1 times 1 is 1 in parentheses. And then plus 6 times k plus 1 squared, isn't that k squared, plus 2k plus 1? All of that is over 6. Any issues with that so far? Okay. Yes, good. All right, so then I'm going to leave the right side alone for right now. K plus 1, k plus 2, 2k plus 3, all over 6. I'm trying to figure out what I want to do next. You know what we could have done?
In the end, do
You know what we could have done that was easier? I'm just thinking. I hope you did in pencil. You're going, no, I didn't. Look what, and tell me why this would be easier. Why is it not erasing? Why did that not erase? Oh, goodness.
Wait, are they supposed to equal each other?
Hmm?
The answer they end up equaling each other?
Oh, your sign. Are they supposed to do what?
Are they supposed to equal each other? Like, do they in the end, or is this something that doesn't?
I don't know why that won't erase. Look at that. Say that again.
Are they supposed to equal in the end? They don't answer.
They will equal at the end, yeah. All right, so let me just ponder this for a moment. See this term here, how it has a k plus 1 in it, and see how that has k plus 1 in it? And the only reason why I say that is because there's no k cubed here, and we're going to end up with a k cubed at some point. So I think it'd be easier if I just factored out a k plus 1 from here and a k plus 1 from here. And you'll see why. So let's factor out a k plus 1. So I'm going to take that out in front, k plus 1. And then tell me, what do I have left here if I take out a k plus 1? What do I have left? I have a k, right? And I have a 2k plus 1. So I've got k times 2k plus 1. Plus, what happens here if I factor out a k plus 1? What do I have left? A 6, right? And one of the k plus 1s. So I have a 6 times a k plus 1. In parentheses, all over 6 because they're both over the same denominator. Do you see how I have a k plus 1 on the left and a k plus 1 on the right? So all I have to do is make this part become what? That right there. And so that's why I decided to erase and do that little step. It is, because I'll have quite a few less steps here. So I'm going to go ahead and distribute. I'm going to distribute this and distribute this. So I end up with k plus 1 times 2k squared plus k plus 6k plus 6 all over 6. And no, you can't get rid of that all over 6 by multiplying both sides by 6. You cannot do things to both sides. This is not, we're not solving, we're not using algebra, nothing like that. So I only have 2 steps left. I'm going to collect like terms here. And so I get k plus 1, I get 2k squared, the k in the 6k is plus 7k, plus 6, oh that's not a k, 7k, all over 6, and then here's how I shorten my workup. K plus 1, k plus 2, 2k plus 3, all over 6. Ask yourself the following question. Okay, so the easiest way to do your final step is ask yourself, obviously we both have a k plus 1. You want to double check and make sure that this foils out into this. Does it? K times 2k is what? 2k squared. K times 3 is 3k. What's 2 times 2k? 4k. Doesn't that equal 7k? And then 2 times 3 is 6. So can't I just write this left side exactly like the right side and be done? In this order, you have to have it in that order because you can't change the order, otherwise it really doesn't physically look like the left side. And so our final answer is k plus 1 times k plus 2 times 2k plus 3 all over 6 is exactly equal to k plus 1 times k plus 2 times 2k plus 2k plus 3 all over 6, and Patrick's hand should be going up right about now. Because your question should be, is that the only way to do this?
No, it's the other way.
Correct. So long as your left side looks identical to your right side and you haven't done the same thing to both sides of the equal sign, in other words, you're not using algebra across the equal sign, Are you with what I'm saying and what I mean? You're just trying to make the left side look like the right side. You can work on both sides, but I caution you to minimalize one side versus the other. And you're just trying to make your life easier, but you can't multiply both sides by something, you can't divide both sides by something, you can't add or subtract something to both sides. You're not solving an equation, you're proving something. So, any other questions? And I'm going to put what Patrick put up here in just a minute. Any other questions? Yes. That's not the question I wanted.